Okay, Math 8 students, we are here in our final lesson of Module 10, Lesson 10.3, Similar Figures. Taking a look at our essential question, this is going to help guide us as we go through. What is the connection between transformations and similar figures? So real quick, just a little tangent here, figures that are similar are same shape but different size. So as we go through and we're looking at the connection between transformations and similar figures, you need to keep that in mind, right? And our transformations include translations, reflections, rotations, and dilations. So in our Explore Activity 1, we are combining transformations with dilations. So when creating an animation, figures need to be translated, reflected, rotated, and sometimes dilated. As an example of this, apply the indicated sequence of transformations to the rectangle. Each transformation is applied to the image of the previous transformation, not to the original figure. Label each image with the letter of the transformation applied. So as we go through this, it's not applied to the original, it's applied to the one we just made. So our first transformation that we are looking at is a translation, and it's a translation of 7 units right and 2 units down. Okay, and we can see that because that's what that algebraic expression shows us. So we're going to take this rectangle right here. We're going to go 7 units to the right. So I'm going to just use this corner right here. 1, 2, 3, 4, 5, 6, 7, and 1, 2 down. And so then you want to make sure that you translate each of those points that same amount. So this would be rectangle A. And we know it's A because it is our transformation A. Okay, then we're going to go ahead and do our transformation for B, which is a reflection across the x-axis. So I'm going to count my perpendicular distance from my line of reflection, which in this case is my x-axis. 1, 2, 3, 4, and I'm going to go 4 in the opposite direction. 1, 2, 3, 4. And draw my rectangle. And this is going to be rectangle B. Okay, so that one's done. And then I've got a rotation 90 degrees clockwise around the origin. So clockwise is this direction, and the origin is our center of rotation. So I'm going to take this point, this line right here, and I'm going to rotate that around the origin 90 degrees. And so this is going to be my rectangle C. My next transformation is another translation. I'm going 5 units right, and I'm going 3 units up. Okay, so I'm going to take this point right here and I'm going to go right 5. 1, 2, 3, 4, 5, and up. 1, 2, 3. And that's going to be rectangle D. Okay, so my last one here looks like a dilation, because it's my algebraic representation for a dilation of 3 times the scale factor of 3. So I'm going to multiply each of my coordinates by 3 to get my scale factor. So since I know my scale factor is 3, I know that my side length when I'm done should be 3 times my side length, right? So I'm going to find my coordinates of each of these 4 points, multiply them by my scale factor, and that's going to give me my coordinates of my next of my image for my dilation. So I'm looking at this point right here, which is 1 and 2. And I'm going to do this point, which is 1 and negative 2. And this one is negative 1, negative 2. And then the last one here is negative 1 and positive 2. I'm going to multiply each of these by my scale factor of 3. I know it's a little tedious if you guys are listening to this, but you can be following along, should be following along doing this with me. Multiplying each of these coordinates by the scale factor. That's positive 2. Okay, so 3 times 1 is 3. And 3 times 2 is 6. 3 times 1 is 3. 3 times negative 2 is negative 6. Okay, make sure you are not losing those negative signs as you go through here. That was some errors that we were having some trouble with as we talked about this in class. 3 times negative 1 is negative 3. And 3 times negative 2 is negative 6. And then our last pair here, 3 times negative 1 is negative 3. And 3 times 2 is 6. Okay, so those are our new coordinates. And we should, that's for rectangle E, we should be able to graph those now. So I've got 3 and 6, so that's going to be right here. 3 and negative 6. It's going to be right, that's 4. Right here. Negative 3, negative 6. And positive 3, negative 3, positive 6. Okay, so I'm going to connect all those points. And this is my double check here. I'm just going to make sure these side lengths, these corresponding side lengths, are 3 times the size. So this is 2 here, 2 units. This should be 6. 1, 2, 3, 4, 5, 6. This is 4 units here. 3 times that would be 12. So this side length should be 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is the right size. And this is our rectangle E. Okay. List the coordinates of the vertices of rectangle E. Oh, we already got that. So we can go ahead and just list what we've got from over there, over on the right there. So we've got 3 and 6. Then we've got 3 and negative 6. Got 3, negative 3, negative 6. And lastly, we've got negative 3 and positive 6. Okay, and the last step here of this one is to compare the following attributes of rectangle E to those of the original figure. So rectangle E to our original figure right here. Is the shape the same? The shape is the same, so this is the same shape. Right? Size. So how does the size of E compare to our original? Well, it was dilated by a scale factor of 3. So we could say something like the side lengths of E are 3 times the side lengths of the original, right? Or 3 times the length times of the. We could also say enlarged by a scale factor of 3. Right? Okay, and angle measures, okay? We know that if the side lengths are proportional to the original, right? The side lengths are proportional, then the angle measures should be the same. So angle measures are the same. Okay, so let's go ahead and see what they want us to do with that information on these reflect questions. So reflecting on that explore activity, which transformation represents dilation, and how can you tell? Well, we know that the algebraic representation of dilation is when we multiply our coordinates by our scale factor. So the one that had x and y to 3 times x and 3 times y is going to be our dilation, because this is the algebraic form of dilation. Right, because the algebraic form of dilation is x and y to k, being the scale factor, times x, and k, being the scale factor, times y. So in this case, k equals 3. Scale factor equals 3. Number 2, a sequence of transformations containing a single dilation is applied to a figure. Are the original figure and its final image congruent? Okay, well, what does congruent mean? Congruent is same size, same shape, right? So since it's been dilated, it's not going to be the same size, so it can't be congruent, but it can be similar, right? So no, because the dilation shrinks or enlarges a figure, right? And so it would not be the same size. Therefore, they would not be the same size. Only the same shape. Okay. So we're actually going to move on to the next part here, example 1, which talks about similar figures. Okay, and these examples are really, really wordy, so I'm going to kind of skim through them a little bit and give you the essential information from them. First of all, it's going to remind us what similar figures are. So 2 figures are similar if one can be obtained from the other by a sequence of translations, reflections, rotations, and dilations. Similar figures have the same shape, but may be different sizes, okay? So when you are told that 2 figures are similar, there must be a sequence of translations, reflections, rotations, and or dilations that transform one into the other. So if they're similar, you have to be able to get that second figure from a series of transformations, which may or may not include dilation. So what it wants us to do in these examples is it wants us to identify a series of transformations that gives figure A, that starts with figure A and results in figure B, okay? So first of all, we know there's a dilation involved, and if we look at trying to determine our scale factor, this has a side length of 2, and this has a side length of 4, which means it's been dilated to a scale factor of 2, right? Because 4 is twice 2. So we know that there's at least a dilation. We also know that there has been probably a translation. There's been a slide somewhere, right? Because if we were to connect our vertices here, they need to intersect at the center of dilation, which with everything that we're working with right now, it has been the origin, okay? So that first dilation would be right here, right? So that would be that enlargement, my scale factor of 2. And then, let's say this point to this point, we have to go 1, 2, 3, 4 right, and 1, 2, 3, 4, 5, 6 up. So dilated by 2, and then translated 4 right and 6 up. So that would be x and y times 2x and 2y, and then x and y, x plus 4 and y plus 6. That would be our sequence of transformations for that one. We're going to take a look at one more for our series of transformations. And so we know that there's a dilation that happened here if we look at it, right? Because we're going from C to D. We know there's been a change in size, and it got smaller, so it's going to be a reduction. If we compare our side lengths, this has a side length of 4, and this has a side length of 2. It's 1/2 the size, right? It's been reduced by a scale factor of 1/2. So that transformation would be 1/2 x and 1/2 y. And you could use the decimal form for that too if you wanted. And if you did, that would be x and y to 0.5x and 0.5y. Either one is correct. You can do whichever one you'd like for that one. Okay, so we would need to reduce it. And then there's also been, notice the orientation has changed. So there's been a reflection, and there's also been a transformation. So we've got a scale factor of 1/2 centered around the origin, followed by a reflection, and then followed by a translation. So there's several in here that happened and that produced our similar but not congruent figures. Okay? So then they give you another scenario here, and you can read through that, but I hope you're getting the idea as we go through. What you need to do now is the your turn, and it's going to have you look again at Explore activity and try and determine another series of transformations, another sequence of transformations that would result in that. And we'll talk about that again in class when we meet next. So hopefully we got a little bit of an idea of how we're producing similar figures through series and sequences of transformations that may or may not include dilation.